Good afternoon or good morning, everybody. It's a rainy and gray day today in Geneva, but still it's a great opportunity to present some new ARPES result on strontium-2 ruthenium-04. What we look at is the temperature evolution of quasi-particles and how you go from a well-characterized Fermi liquid state at low temperature to a bad metal state at high temperature. So this work was actually the PhD project of Andrew Hunter in the ARPES group here in Geneva. And we collaborated with Sophie Beck, Antoine at the Flatiron Institute, and Yerny Mraliev at the University of Ljubljana. And the samples that we measured were grown by Dmitry Sokolov at the Max Planck Institute in Dresden. So strontium-2 ruthenium-04 is, I think, a model system to understand the interaction in a multi-band system. So it's a layer perovskite. The conduction electron lives in this ruthenium oxygen 2 plane and are separated by strontium oxygen rock salt insulating layers. So this results in a very anisotropic electronic structure. And the interest in the material came from the observation of unconventional superconductivity. It was one of the first layer perovskite, other different than cuprates, to show superconductivity. And since nearly 30 years, people are still discussing what is the symmetry of the order parameter in strontium-2 ruthenium-04. It was thought for many years to be a candidate for P-wave superconductivity. However, recent experiment under strain questioned this idea, and people are still discussing what is the symmetry of the order parameter. My talk won't be about superconductivity, it will be about the normal state. So it's a very clean and well-characterized Fermi liquid at low temperature. The mean free path is several micrometers, so it's very long, huge. And it shows T-square resistivity below 25 Kelvin, both in plane and out of plane. As you warm up, you observe first crossover along the C-axis into an insulating state, whereas the in-plane resistivity keeps on increasing. And at even higher temperature, this resistivity never saturates, so it keeps going up beyond what is the Motti-Offer-Regel limit. Here you have a different definition. The resistivity increases, and the mean free path becomes much smaller than what is the size of your Brillouin zone. This situation is described as a bad metal. It's a state where you should not expect to have quasi-particles, because indeed the coherence length of this quasi-particle is much smaller than the size of your Brillouin zone. It's not an exception to observe a bad metal state. Actually, there are it's quite common also in cuprate, iron, pnictides, manganites, fullerenes, organics. Now the question is how you go from this low temperature Fermi liquid state into this high temperature bad metal state. Are there still quasi-particles as you increase temperature, and how do they behave? So a few things about the low temperature Fermi liquid state. It's you have 4 electrons in a 4D ruthenium shell, which are distributed over the 3 T2G orbitals. And the Fermi surface, as you see it here in the center, it consists of a large circular Fermi surface called gamma and 2 square-like pockets called alpha and beta. This was the first measurement of the bulk Fermi surface from ARPES by Andrea Damascelli. 20 years later, same material looks like this, measured by laser ARPES in our home lab. And the measurement became much more accurate because we use lasers as excitation sources. So we have a higher energy and momentum resolution, and also lower temperature. So the data quality improved, and we were able to address two questions from this data set. What happens of spin-orbit coupling, what is the effect of spin-orbit coupling at the Fermi surface, and how the self-energy or the many-body interaction behave as you move, evolve as you move along the Fermi surface. So I will go quickly through these 2 points. So spin-orbit coupling. If you do a DFT calculation without spin-orbit coupling, you would expect at some point on the Fermi surface, and that's what you see here. There are points where the gamma and the beta Fermi sheets should be degenerate. When you measure, you find a larger splitting in momentum between these two bands, and the splitting comes from spin-orbit coupling and is partially described by a calculation that an LDA calculation that includes spin-orbit coupling. However, in experiment, the splitting is twice as large than what you would expect from LDA plus SOC. And this increase of spin-orbit coupling is actually due to correlation effects, what was found by Min-Jae Kim and Antoine a few years ago, is that DMFT finds off-diagonal terms in the self-energy, which are consistent with an increase of spin-orbit coupling due to correlations. And if you include this enhancement of spin-orbit coupling, you end up with an Hamiltonian that describes very accurately the Fermi surface of strontium-2 ruthenium-4. So from now on, I will consider this my bare Hamiltonian, an Hamiltonian that has spin-orbit coupling, but the effect is enhanced by correlations. The second thing we look at is how the dispersion of the quasi-particle dispersion evolves as you move on the Fermi surface. And here you have a few dispersion plots starting from the gamma M direction into the diagonal of the brilliant zone. So when you look at the gamma M direction, you see only the beta and the gamma band, and you see that the velocity of these two bands is quite different. And as you move towards the diagonal, you actually see that the two bands have basically the same velocity. So there is a strong angular dependence of these velocities. You can do a bit more accurate analysis and extract what is the self-energy as a function of angle or as you move on the Fermi surface. So we extracted the dispersion from ARPES and we compare this with our the dispersion from the bare Hamiltonian, which again includes an enhancement of spin-orbit coupling due to correlations, but this effect is frequency independent. So you see that the self-energy is quite different when you from between the gamma and the beta band along the gamma M direction. The real part of the self-energy is much higher for the gamma band. And as you move towards the diagonal, the two become quite the same. Now you should wonder what is the origin of this strong angular or momentum dependence, and whether this is an indication of non-local interactions. And indeed, when we put all this data together, we were quite puzzled, because now I'm overplotting all the self-energies from the beta and the gamma band extracted along different directions, and you end up with a very complicated plot. Depending on which direction you look, you get different real part of the self-energy, indicating that there would be an angular or a momentum dependence. However, you should consider that a consequence of spin-orbit coupling is to produce a strong orbital mixing along the Fermi surface. And if you look at the problem, instead of what is the band basis, alpha, beta, gamma Fermi sheets, you look at the problem in the orbital basis. So what is whether these states have either dxy, dyz, or dxz orbital. You see that this complicated picture immediately collapses into two well-defined self-energies, one for the dxy and one for the out-of-plane dxz, dyz orbitals. And this is also what single-site DMFT finds. So what we extract from experiment is in very good agreement with a calculation that consider only local interactions, which settle a bit the stage. we can describe the Fermi liquid state of strontium-2 ruthenium-4 with a bare Hamiltonian that includes spin-orbit coupling enhanced by correlation, and the evolution at the Fermi surface is consistent with a dominant role of local interactions. Now the question is what happens when you increase temperature, how this system, this state that we kind of understand evolves. And the questions are two: are there still quasi-particles when you move away from this low temperature Fermi liquid phase? And if there are still quasi-particles, how do they behave? So the quantity that I try to extract from experiment to measure how healthy these quasi-particles are is the quasi-particle residue Z. And if you know, if you have the self-energy, you can define the quasi-particle residue Z from the slope of the real part of the self-energy. This is the definition. You take the slope at omega equals 0, and you get the quasi-particle residue. The higher Z is, the less strong interactions are, the more important interactions are, the smaller will be Z. And this value also results in what is called the mass enhancement, so the ratio between your Fermi velocity and the velocity in the non-interacting picture. This is one definition. A different one, and we'll discuss how equivalent is to look at spectral weight. And this is a picture that is actually quite used in the ARPES community to extract the quasi-particle residue from the integral of the coherent part of the spectrum. As you increase correlation, your spectral weight distributes differently between a coherent part and an incoherent part. So this problem was already looked at a few years ago in the group of Peter Johnson. They looked at how quasi-particle evolves with temperature. These are some of their data. So it's an EDC, an energy distribution spectrum measured at a specific point at the Fermi surface for the 3 different temperatures. They assume some background and they extract the coherent part of the peak. And then they plot this as a function of temperature, and they observe that these quasi-particles, first they are basically not, this peak gets broad and is hardly visible at high temperature. And they conclude that quasi-particles tend to disappear at the temperature where there is a crossover in resistivity along the z-axis. And they say that Z goes to 0 as you increase the temperature. This picture that Z goes to 0 as you increase the temperature is not unique of strontium rutheniate. It is actually found in many ARPES papers on different materials. Here there are 3 examples on cobaltate, iron pnictides, the surface states on strontium-2 ruthenium-4. And you find often in the literature plots where they derive the quasi-particle residue Z, and they conclude that as you increase temperature, Z goes to 0. Fine. Then these are the experimentalists and what DMFT or what theory finds. I have here 2 cases. So I took this from recent calculations from Yerny Imraliev. You take the Hubbard model at half filling, and you get you extract a Z from the slope of your of the real part of the self-energy. As you increase U, eventually the system you will enter into the insulating phase, so Z will go to 0. If you stay at the moderate U, so before this metal insulated transition, these are some of the spectra that you obtain. So there is a quasi-particle peak and a lower and a upper Hubbard band. And when you extract Z, you find that Z actually increases with temperature. The same is found in a completely different system. So the system we are studying now, which is a multi-orbital Hons metal like strontium-2 ruthenium-4, where for the 2 orbitals in both cases, you find that Z increases with temperature. And it seems a common picture in DMFT that as you increase temperature, these quasi-particles tend to behave more and more like non-interacting electrons. So we have okay, the only case we found where you find in theory and probably in experiment a case where Z goes to 0 as you increase temperature, is if you are very close to the metal insulator transition. And this is the case of these organic salts. They have a finite resistivity at low temperature, then the resistivity goes up and decreases as you increase temperature. Z goes to 0 because you eventually enter into an insulating state. This is not the case in the rosinate. They are very good metal up to high temperature. So there is clearly a bit of a problem between an experiment that says that Z goes to 0 as you move away from the Fermi liquid into this bad metal phase, and experiment that says that Z should go to 1 or should increase. So we look at this problem with a new set of measurements. So we start with some simple spectra at low and at high temperature. At low temperature, you have a very high, well-defined quasi-particle peak. At high temperature, above this crossover into the insulating state along the z-axis, there is still a tiny peak in the spectra. Now, what is Z? If you would extract Z from the spectra, following what many ARPES group did, you would consider this intensity here at high energy like as your background, and you would say, okay, this is my quasi-particle peak for this temperature, and this little peak is what is left at high temperature, so Z goes to 0. The problem is that experimentally we have not much control and understanding of this background, and you could imagine that actually here the background goes down much faster to the Fermi level, and this could be your quasi-particle peak. And if you do the same at high temperature, you may find a background for which Z will be constant as a function of temperature. We concluded from this that it's actually quite difficult to extract Z from just by looking at the spectral weight. And we proposed a different approach, which was to look at the dispersion, at how the mass enhancement changes with temperature. So here is a set of measurements from low to high temperature. You see that there are low temperature, well-defined bands dispersing. Things get broader as you warm up, but still at 200 Kelvin, there are still defined features that you could describe as quasi-particles. So the first observation was from this dispersion plot is that the quasi-particle survives up to high temperature. So if you take a cut here, you find a well-defined peak for all these temperatures. Even they survive at high temperature beyond this Fermi liquid regime. Second thing is what happens of the dispersion. So we try to extract Z from the mass enhancement, and we look at how the dispersion of these bands changes with temperature. We can take a cut at constant energy, then you would get these 4 peaks for the beta and the gamma band. And then the idea is sketched here on the right. If the mass changes as a function of temperature, here I approximate with just a simple parabola, you would expect the position of these peaks, for instance, down here, to change with temperature, describing a change in of the mass with temperature. So we did this type of analysis here at the Fermi level and a bit below. And this is the result. So at the Fermi level, the plot refers only to the gamma band. We see that as you increase the temperature, there is a small change in the Fermi wave vector, and this is consistent with a small deflation of the Fermi surface. If you repeat the same analysis down here, you find the opposite trend. And this trend can be described in the sketch here. It's consistent with the mass of this gamma band to become lighter as you increase the temperature. We repeat the analysis for the beta and the gamma band and use this data set to evaluate the effect, the Fermi velocities, and we extracted Z. So what we observe then from the analysis that Z extracted in this way from the mass enhancement increases with temperature, increases this, with temperature both for the gamma and the beta band. And this analysis is done for what we call the band basis for the gamma and the beta. We can also compare this with what is found by DMFT. In this case, in the orbital basis, if you look here at the real part of the self-energy for the dxy orbital, you see that the slope of the real part of the self-energy changes with the temperature, and it becomes less steep the more you go to higher temperature. And we know what is the orbital content along the Fermi surface. dxy is the dominant orbital character for the gamma band, and this is consistent. So this increase in Z is consistent with what we also DMFT finds. So it is not true that quasi-particle disappear as you move away from the Fermi liquid into this bad metal state, because Z goes to zero. Z actually increases, Z doesn't go to zero. We find that quasi-particle seems to disappear as you increase temperature because of their broadening, excessive broadening. So what we did, we extracted the quasi-particle lifetime. This is for the gamma band as a function of temperature, and we see that this increases very fast with temperature. So they don't, these quasi-particles don't die by losing spectral weight, but by becoming so broad that they kind of disappear into the background. This quasi-particle lifetime actually reproduce quite well what is the temperature dependence of the resistivity. So we used the quasi-particle lifetime to calculate the conductivity, and these are the experimental values from ARPES overplotted over the resistivity. What we are comparing here is also what the DMFT finds. DMFT seems to find a slightly smaller quasi-particle lifetime than experiment. Of course, in experiment, there will be more effect than just electron-electron scattering. There will be also electron-phonon scattering. And indeed, there is this is a recent DMFT work that also includes electron-phonon coupling. There is a small increase, an additional increase due to electron-phonon coupling, but this is actually quite small. The dominant effect is electron-electron scattering. Okay, so at this point we were kind of happy because we had some understanding of how Z goes with temperature, but we were still wondering whether there is a fundamental issue between calculating Z from the mass enhancement or calculating Z, extracting Z from the coherent part of the spectrum. And so we did we test this by looking at the DMFT spectral function where there are no experimental issues or artifacts. So these are spectra calculated by DMFT at a particular point at the Fermi surface where you would have three contribution from the alpha, the gamma, and the beta band. And we look at the peak that derive from the gamma band, and we fit an error range around the peak to extract what is the quasi-particle weight. Then we compare, and what we obtain is actually that if you do this, you see that Z defined as the integral of this peak increases with temperature, and this is consistent with what you also find if you start from the slope of your real part of the self-energy, which is the blue line. The problem in experiment is actually the experimental background and how difficult or whether it's possible or not to separate in experiment what is the coherent part of the peak from the incoherent part. So we took slightly different approach at what was done in the past. We extract, for instance, an EDC here for the gamma band. And as a background, we took an EDC at the position in momentum where there are no states, and use this as our background. Then if you subtract the EDC at this position, the EDC at the red position, you see that even at relatively high temperature, there is still a small peak remaining. And we did this analysis for several different temperatures. So here are these background subtracting ARPES data. And what we actually find is that these data are very consistent with what DMFT also observed. So the solid lines that you see here are not fits. These are DMFT spectral function that were calculated at different temperature, multiplied by a Fermi function, because in ARPES we only probe the occupied states, and then convoluted with a Gaussian that takes into account experimental broadening. And you see that the temperature evolution of these quasi-particle peaks seen in ARPES is well captured by the DMFT calculation. So I think I am on my last slide. These are my conclusions. So I discussed with you how quasi-particle evolve with temperature in strontium-2 ruthenium-4. I show you that this quasi-particle-like excitation survive in the non-Fermi liquid regime. And I look at two things, Z, so the mass enhancement and the lifetime. And as we increase temperature, we find that Z increases. So these quasi-particles tend to become faster and faster, and the scattering rate goes up. So I like to call them fast and furious quasi-particles. And that's the excessive broadening is the reason why they tend to disappear as you move into the bad metal state. And I discuss with you spectral weight, and I show you that at least from experimental point of view, it's quite difficult to extract reliable values from this. And with this, I hope you are still there, and I thank you for the attention.
Thank you very much, Anna. This was a very beautiful talk. I'm also glad that we started this session with experiments. It's a beautiful example with where DMFT calculations have changed the consensus on how photoemission experiments can be interpreted. So it's a beautiful example of synergy between theory and experiments. And the talk is now open for questions. So Olivier and Jean-Guy and Olivier Parcon are going to handle the questions, which says in statistical physics, the expectation is that correlation effects become smaller and mean filtering more appropriate when temperature increases. The spectral comparisons here seem to support this. Would you say this is correct?
Yes, that's exactly what I wanted to say. So DMFT or mean field theory finds that correlation becomes smaller, and I said they become smaller. I illustrate this by saying Z increases, so that goes to nearly to 1. The analysis of the experiment seems to support this. So both the mass enhancement become smaller, which is consistent with the Z increasing. So yes, that's exactly what I wanted to say.
But would you say also that the agreement between DMFT and the experiment becomes better at higher temperature? Or is it just the same everywhere?
No, I wouldn't say it becomes, no, on this I would not comment. I would say that we see the same trend. I mean, this is maybe illustrated here. I don't think we see the same temperature evolution. Whether the agreement gets better at high temperature, I can't say. I don't know.
Okay, for the next question, Cyrus will ask the question. Cyrus Ryan.
Yes, Thanks. So I was just wondering if this gives any insight into why certain materials have resistivity saturation and certain materials don't. So is the suggestion that the non-saturation is because the quasi-particle weight is actually not disappearing, and when it saturates, it is?
I think when it's saturated, it means that this mean free path remains quite large. So you the mean free path remains large. You will, so if you take a good metal, I don't know, if you take copper, copper doesn't, the resistivity doesn't saturate because it melts before you reach that regime. But if you take I know there was early work on some material that shows resistivity that saturates, they will have very low, still quite long mean free path, which means that there are well-defined quasi-particle up to high temperature.
For the next question, we have Waiting Lin. You've been
Yeah.
unmuted. You want to ask?
Yes, thanks. First, thanks for this very interesting talk. I really like it. So I'm curious about the scaling at like in the range between 100K and 200K. I think you show a plot that it looks like a quadratic. It's quadratic in temperature. Yeah, I don't remember which slides.
Show resistivity, maybe.
Yeah, resist. Not at the beginning. I think it's late. I think it's at the end of your talk that you show the experimental data that even at high temperatures, it seems either the scattering rate, h bar over tau, which is a scattering rate, and it looks like a quadratic. Is that correct? Because on that slide there's no fitting curve.
Yeah, I see. So this, okay, this
yes,
is
yes, that is the one
so it's so this is scattering rate for the gamma band as a function of temperature. I think so it would be it's a Fermi liquid below 25 Kelvin from resistivity.
Yes.
We don't have many data at very low temperature. It looks like so this would be linear in temperature.
Yes.
It is probably it is it goes like T squared at very low temperature. We pick up very little of these temperatures, and then it increases much faster.
So but it looks like this data point, it looks like also T squared, but maybe with a different prefactor. Did you try to fit those RPS data points?
I think yes. I think it goes to like T squared at very low temperature. Then
okay. Then do you like have any idea about the scaling at this high temperature regime?
We didn't look at that. We would have to do it as a function of temperature and as a function of frequency. That's what you would like to do.
Okay, but you think it's so in this regime the electron-electron interaction or electron-electron scattering is a dominating
yes, I think it is the dominant the dominant factor. It's also it seems that the electron photon coupling does a small contribution to the scattering rate. So
okay, thank you. Very interesting results.
Okay, thank you for the question. Next question will be Seyong Park.
Yes. Yeah, so my question is kind of related to other two previous questions. So if I understand correctly, the quasi-particle is well defined in high temperature, but somehow there is very fast scattering process. Still, you can get the bad metallic. So this seems to be different from conventional understanding. So do you have any idea what would be the scattering mechanism? Like you just mentioned the electron-electron scattering, but what about the phonons and other new type of scattering mechanisms?
But so okay, let's look at this. So here I'm comparing experimental scattering rate with, for instance, what is found by DMFT, which is a calculation that includes only electron-electron interaction. I would say that experimentally we find a higher scattering rate, which could be at a little bit the additional contribution of electron phonon scattering. The picture is that is well, I don't have a picture of the scattering mechanism, but I would say the idea is these quasi-particles are still well defined, but they become so broad because of the excessive scattering that they kind of disappear in the spectrum. They are with temperature.
Okay, thank you. Yeah.
Okay, next question by Dita.
Hello, Anna, this was a wonderful talk, very clear, thank you very much. I still have a question. You call quasi-particles fast and furious. Furious, okay. Could you quantify fast again?
Faster because exactly, I have a lot of windows from, let's go back. I would say I would call them faster because as I increase temperature, Z is higher, and higher values of Z means that the mass enhancement gets smaller. So these quasi-particles become faster as you increase temperature compared to how they behave at low temperature.
Okay, I understand. Thank you.
Sasha, you can ask the question.
Okay, great. Thank you. So if I look at this exactly at this plot, so DMFT is more correlated by 30-40% than experiment. So it's probably depends on you, which was used in DMFT. But this you could fit. But what is more important probably for theoretical community is interest in 3-band model. Do you still, and you have a very enhanced accuracy in ARPIS, do you still have some sign of K-dependence of self-energy? I mean, beyond.
Okay, so first comment on the fact that we find higher values of Z than DMFT. I think this is an experimental issue. I think what you should take of this graph is mostly that DMFT and ARPES find the same temperature dependence. On the exact values of Z that we extract from the experiment, there are a lot of issues on the resolution of the experiment, on how you prepare the system to show the bulk states and not the surface states, and it's extracting Z from experiment relies on a very accurate measure of the velocity, and it's very difficult to measure the velocity for the gamma band, which is close, which has a van Alve singularity very close to the Fermi level. So there are experimental issues on extracting the velocity. So I would not. I would blame this difference on I think on the experiment. We did the measurement at lower temperature and with higher resolution, and in this set that show the values, experimental values of Z very close to the MFT.
In fact, Anna, if you allow me to intervene, this is Antoine.
Yes.
Quantum oscillation, I mean, this is exactly what you said, but the quantum oscillation measurements for the gamma band are closer to 0.2 indeed.
Yes. The second point was whether there is still some momentum dependence. what can I say? So we look at this at low temperature. So here you see a comparison of ARPES derived real part of the self-energy with DMFT that considers only local interaction. The non-local interactions are probably I mean, I judge this agreement already I find this agreement already very good, but probably there are additional interaction because we know that there are spin fluctuations in this system, but the effect seems to be quite small, or it's an additional effect, but the dominant effect is described by this local DMFT self-energy.
Okay, thank you.
Okay, thank you very much, Anna, and we are all grateful for a very nice talk.